thank you all for coming. I hope you had a great lunch. I certainly did. I'm here to tell you about microservices at Nedap Retail. This is a picture of our office. It's a happy office, I might say. And the company was founded in 1929. We started in Amsterdam as the Nederlandse Apparatenfabriek, which is something like the Dutch devices factory. Back then we started creating machines, parts for machines, etc. That's not what we do right now. It's more like services, software, both software and hardware. There are about 600 people working in Groenlo, which is somewhere in the middle of nowhere in the Netherlands. And we're divided into 9 market groups. Each market group makes solutions, services for a specific market. We start with retail. That's where I'm working, so I will come to that, back to that later. We have identification systems, which can identify vehicles, drivers of vehicles, empty parking spaces. We have the library systems, which make systems that can identify books. So when you are in the library, you picked out your books, you put a pile of books on the desk, and the system knows which books you want to take home with you. Same for bringing them back. It's just enough to put them on the desk and you're done. We have energy systems, which makes a smart grid solution to share energy between houses. For example, if your neighbor has solar cells and you have a windmill, then you can share energy if there's wind but no sun, or the other way around. We have Netapp Security for securing access to buildings. For example, we secure access to Porsche factories, to the Eiffel Tower in Paris. We have Nedap Healthcare. Oh no, this is Nedap PEP actually, which is registration of hours made by employment agencies. We have Nedap Light Controls, which makes electronics and software to control lights, mainly in large buildings, like halls like this, but also factories. We have Nedap Healthcare, which just does time registration and planning for people, taking care of people at their own homes. And we have Nedap Livestock, which has technology to identify and monitor pigs and cows. So the red thread between all of these is mostly identification of products, humans, whatever. At Nedap Retail, we supply store technology for mainly fashion stores and hypermarkets, so very big supermarkets. And we are in Europe the #1 store technology provider. Although we are #1 in Europe, we deliver all over the world. That's why we have 3 support offices, one in the US, one in Europe, and one in China, to be able to deliver 24-hour support. Although all product development is done in the Netherlands, we have a worldwide network of offices and partners that do the support, the installation, and sales. We have 2 main products. The first one being anti-theft systems. Here you see these pedestals you see at the entrance and the exits of shops, and they will beep when you try to steal something. They can actually do more than that. they can detect metal, because if you put anti-theft tags into a metal bag, they won't be detected anymore, but we can detect the bags. It has infrared sensors for customer counting, so you can count your customers, and they're all connected to our device management solution to monitor the status of these devices, and they send their data to our Nedap Retail analytics software, so that the retailer can log in and see how many customers there are in each store, and if, for example, if his personnel planning matches the peaks in visitors. The other product we make is stock management. And we do stock management using RFID, where the normal, the old-fashioned anti-theft tags were just RF tags, so they can be detected if there is a tag or there's no tag. The ID has an identification in the unique number. You see an example of such an RFID tag here. Most of it is the antenna, and this little black dot is the chip. The readers used to read this kind of tags emit an electromagnetic field, which is picked up by these huge antennas, which powers the chip, which then sends back its unique number. For fashion retail, this RFID chip is usually embedded in the price tag. The number that's encoded into the chip is usually the barcode, which identifies what type of article it is, and the serial number, which makes this exact item unique. So you could say the barcode is the class and the serial number makes it an instance. This property that each tag is unique makes it very suitable for doing an inventory count in the store. It's really nice for retailers to know what's inside their store, because what's not in their store they have to order, or maybe they don't have it on the sales floor but still in the stock room, but then they won't sell it because the customer can't see it. Where there's usually one time per year, usually at the end of the year, a manual count in each store. People who have worked in stores probably know this, that it's a lot of work, error prone, so it's only done once per year, which means that the stock data of the retailer is only updated once per year. And during the year, the accuracy of this stock data gets worse because of theft, because of mishandlings by the cash register. For example, somebody buys a red and a blue t-shirt, and the person behind the cash register thinks, oh, they're the same price, I'll just scan one item twice. Then you have already a stock difference. And things like mistagging, misdeliveries, etc. If you want to have an overview of which item is where at each point in time, you need to have RFID readers on every place where a product changes location or status. So that is, for example, when the items enter the store, when they are from the distribution center sent to the store. Then they're in the stock room. When they go from the stock room to the sales floor, they're scanned again. Because it's nice to know if an item is in the stock room or the sales floor. Because then you can present a list of items that are in the stock room but not on the sales floor. This process is called replenishment. You can take these items from the stock room and put them on the sales floor. The items are scanned when you do a manual scan with a handheld device. They can be scanned at the cash register. RFID makes it possible that when you've picked out a bunch of clothes, you just put the entire pile on the desk near the cash register, and the RFID reader already read all items, so they don't need to be scanned individually anymore. And again, at the exit, if you haven't paid for an item, the alarm will go off. So RFID can also be used as anti-theft protection, which means that you do not have to have a separate process to attach these anti-theft tags anymore. So then you have real-time stock. So you know where each item is at each point in time. It's useful for retailers to know this, and it's because of when they know that the stock in their systems is not accurate, they will overstock stores. So they will send, just in case, extra items to the store. So that will take extra space. These items will be on the shelf, so they won't gain any money by that. So that costs money. When you exactly know what's in stock, you can have less stocks in your stores. The other thing is anti-theft using RFID. If somebody buys an item, then in the database, this item is marked as sold. And when this person runs outside the store, only a couple of seconds later, this item is read at the entrance, and the system should know that it's been sold, and it should not alarm. It also enables new possibilities for retailers. We see a trend in retail that they go omni-channel. So they're not only selling from their stores, but also on their web shops, their mobile apps, everywhere. While this is a logistical challenge for most retailers, they just have an entire separate supply chain just to fulfill web orders, for example. But with this real-time stock, you can put the contents of your store on your web shop, actually. Or you could create scenarios where people buy something on your web shop and don't have to wait 1 or 2 days for the mailman to come in, but immediately pick it up in the nearest store. So in order to make this possible, we've created ID Cloud, which is an integration platform for RFID data. This integrates our handheld reader and app, which we also make at Netapp, our RFID-enabled anti-theft pedestals, which can also be used for the goods receiving and the stockroom to sales floor transition, because the behavior of the system is defined in software. You, of course, have a website where you can view your stocks, your difference lists. The difference list is the difference between an RFID scan and what the administrative stock of the RFID of the retailer is. So using an RFID scan and reading what's inside the ERP system for stock, you can create a difference list. It's a list of differences. And that's actually the items that you want to correct in this ERP system so that the ERP system is up to date. ERP systems are used for all logistic processes, for transport, for ordering goods for next season. Usually the cash register reports to the ERP system. But with RFID, the cash register can also report to ID Cloud to register the sales, which is needed in case of anti-theft. So we have integrated cash registers, ERP systems, handheld devices. We also have integrated other system integrators, because usually ID Cloud is a standard product. The retailer has an ERP system or whatever system he wants to hook up to ID Cloud. We provide APIs. A lot of retailers don't have an IT department or the knowledge to do those integrations, so they hire a system integrator. And these system integrators can work in any language, like Java, Swift, C#. This is why we chose an API-first design methodology for ID Cloud, because the APIs are the central thing in ID Cloud, because it's an integration platform. But actually, this is not the only landscape where ID Cloud is in. It's also in the landscape of other websites and services at Nedap Retail. For example, we have the Cube system, which is a legacy system for access control. We have EasyNet, which is a system for data collection of our previous generation of anti-theft systems. We have retail analytics, I just told you about, with customer counting data, alarm levels, etc. We have device management, which, well, the name doesn't really cover it, but it's used to manage devices, but it also holds all user accounts, organizational data, and things like that. And we have a partner portal for partners who sell our hardware and services and who will provide support. So you can imagine that this organizational information that's here in device management is used by all of these other systems. So then it's a logical step to extract this organizational information from the device management website and make it its own service that's being used by all other services. And then that's actually when you come to microservices. What microservices is we used to make applications like this, one big application with a UI, some processing, a database, all in one. But when you have a larger application landscape, where you can reuse parts, for example, then it's more logical to have a separate processing service with its own database. Maybe the UI is generated or combined by two different services. And this is what we call microservices. So actually it's just a split up of your normal large application. The technologies we use for ID Cloud is our websites are in Ruby on Rails. Most microservices we use are, there they are, Spring Boot applications. We link everything together, so the communication between these microservices is done over RabbitMQ, a message queue system. And we use all kinds of databases, like Cassandra, MongoDB, MySQL, and Elasticsearch. And that's because we think we should use the best tool for each problem. You can have one problem where Mongo is the best, and another problem where Cassandra is the best. Then you should not try to put everything in Mongo or everything in Cassandra. Which is easy by using microservices, because the one microservice can use Cassandra, the other microservice can use Mongo. So what if a HTTP request comes in through our APIs? Well, first time is BAS security, of course. We secure our APIs using open authentication. So an access token is sent with each HTTP request. And this guy then checks if it's a valid token and if you're allowed to call this endpoint. If so, there is some routing involved. The URLs of our APIs are actually formed in the form of, you have a namespace, then a version, and then the method you want to call. So for article metadata, for example, the namespace is articles, then you have the version, and then you have the method, for example, retrieve or update or delete. these URLs are transformed into routing keys for our message queuing system. And basically all API endpoints for the article metadata, the article's namespace, are sent to the articles exchange, where one or more services are listening to. So it looks something like this. I've drawn here 3 microservices, but actually we have more in the order of 40, but that would clutter up too much. We have the gateway that puts messages in the message queue, and we have, this is for example the article manager that handles all article metadata, that reads from this queue, does something with the database if needed, and sends a reply back. If, for example, the EPCIS manager needs article data, then it should ask the article manager and not read from this database. Because if we want to change this database, change the schema, or even change the type of database, then we know we only have to change the article manager. Because we know for sure that no other microservice is reading from this database, which makes happy developers. If we look into this article manager, we see 3 routing keys here. So it's to create or update articles. They're validated, of course, if it's valid data. And if so, it's put in a message queue with a number of workers that puts it in Cassandra. We've put these workers here because saving in Cassandra can take some time. It could be that Cassandra is offline, or there's an error saving and you want to retry. In that case, the message just stays in this message queue. And the client doing this API call doesn't have to be bothered by that. Because as soon as the validation passes, an OK is sent back. From OK, we've received your articles, thank you. Deleting articles also goes through the same workers. Retrieving articles does some parameter validation and then reads from the Cassandra database. But Cassandra is a really nice database in the sense that it scales, they say indefinitely, just add extra servers. But it's a big data database, which means that you have to put your data in like you want it out. So basically, if you want to query your data in 5 different ways, you have to save it 5 times. Which turned out to be not the best choice for article metadata when we wanted to implement a find function. Because it should look for the data in the size column, in the name column, in the price column, the season column, the supplier column, all of those. So we had this microservice and wanted to change it. So what we did, we created a new microservice which took over part of the functionality. This is the new microservice, and we used Elasticsearch. So these articles coming in, being validated, being saved into Cassandra, also were indexed in Elasticsearch. And we rerouted the retrieve endpoint to this new microservice and added the find endpoint. So this was really an easy change in our microservices architecture. When you have microservices, you need to pay attention to monitoring. Because when you have microservices, you have, well, in our example, like 40 services running on one server, and you have multiple servers, so you have 40 times the number of servers on things you have to monitor. What we do is we use iSynga to monitor the bare metal, so to say. So if is disk space okay, is memory okay? We also use it to monitor the message queues, if messages are piling up somewhere in our system. We use New Relic for performance monitoring, because if you have a performance problem, you want to know before your clients start to complain, and it could also be an indication that something is wrong. And we use Rollbar for exception logging, because if something goes wrong, you don't want to have to go through hundreds of log files to see where this error actually happened. But the thing is, these New Relic and Rollbar logging are actually logging when something already has happened. It is reactive monitoring. So that's why we use black box testing. This is a black box, couldn't think of a logo. And what black box testing does is it sees ID Cloud as a black box, and it will only, so it has no knowledge of the internals. It will use its APIs to update data, to put data in, and to retrieve data. And it knows only how the outside should behave. So I put 100 articles in, I should get 100 articles out. And if I don't get 100 articles out, or it takes too long, then I will raise an alert. So actually, these black box tests are using ID Cloud on a regular basis. On production, we have set these black box tests to run every hour, which means that we test our production every hour. And it also means that it is proactive monitoring in the sense that when the black box test sense something has failed, then there is a chance that no client has yet experienced this. So you can even fix it before anybody knows. So why should you use microservices? It's really easy to do multi-team development, because if you have multiple teams, you just assign one or more microservices to each team, as long as you agree on a common set of rules, such as using message queues, formatting your messages in JANSEN, naming of your endpoints, and those kind of things. And you can scale where it needs to scale. If you have this monolithic application and you need more processing power, you need to duplicate the entire application. Whereas if we need more capacity to process article information, for example, then we just spin up on a couple of extra of those microservices or increase the worker pool. So we don't have to scale everything, we just need to scale what needs to scale. Change is easy because microservices are rather small applications. You have an overview of where each functionality is. So you can, if you want to change something, you can easily find where you need to change something. Small deployments. If you want to update your server and you need to deploy an entire monolithic application, it could take a couple of seconds. And how do you make sure that your application keeps running during those couple of seconds? Using microservices, you can just tear down microservice, spin a couple up, doesn't matter, the message queue system will handle that. If a microservice on one server is not available, the message queues are also load balanced on multiple servers, so the same servers on a different server will pick that message up. You have a freedom of technology choice. For each microservice, well, we mainly use Java, but there's nothing prohibiting you to use C# for the next microservice, or Scala for the next microservice, or Python. So you can use the best tool for each job. And it's really easy to do small-scale experiments. For example, you're creating a new microservice that would replace another. You can easily, for example, route 10% of your traffic to that microservice to see how it behaves. But there are also some downsides, of course. First question is, how micro is your service? If you ask the purists, they say, well, microservice should not be more than 1,000 lines of code. But that's a trade-off, because if you have such small microservices, you have overhead, you have a lot more monitoring to do, and in the end, the microservice itself will be nice, and you have a quick overview over that, but you won't have the overview over the entire landscape. You have to agree on a common infrastructure. It's not really good to have one set of microservices use HTTP calls for communication between them, and the other use RabbitMQ, and a third one uses UDP communication or whatever. And you really need to look into DevOps. With microservices, you need to automate everything, because really things can really go to a scale where you are not able to do things by hand anymore. Maybe you are able to do this by hand, but it will take a lot of time. You do not have a guarantee that each service on each server is configured the same, for example. And don't over-engineer. Oh, sorry, monitoring, I forgot. Yeah, I already talked about that. And don't over-engineer. It's really nice to use Google technologies for scaling, like Cassandra, or Kubernetes is now the buzzword at Google. But think if you really need it. For example, if you have a project that spans a couple of months and then runs for a year and is then finished, it's probably, if you don't have a lot of traffic, not worth the effort to do microservices. And if my clicker works, yeah. That's about what I wanted to tell to you. So, I'm curious, are there any questions? Was I clear about a couple of, yeah, they're in the back.
Okay, let me ask you about your microservices. So probably some business workflow, you have a couple of microservices, maybe 10, you know, like chain in a flow. So in case some of them fail, how do you compensate? Because there's not really a transaction, the database transaction going on. So you have different data source. So you somehow need to synchronize and compensate for failures. So that's the question.
Yeah, actually in our application we do not have those chains, so that's easy. We use the reliability of the message queuing system. So if processing a message fails, then it's not acknowledged, so it stays in the queue. So it can be reprocessed by at another time or by a different server. Okay,
so how about storing customer information in one microservice? How propagates? For example, if you change the customer name to other microservices,
it propagates again through a message. We have something called the unified log, which all microservices send their events to. So, for example, there could be an event, organization details changed. So once the saving of this organization details has successfully finished, then this microservice sends a message to the unified log, hey, the organization details for this organization have changed. And all other microservices that do something with this information or should act on this change can listen to the unified log and do something with it.
Okay, excellent, thank you.
Okay. There in the back was another question.
Okay, so what would be the steps in turning the monolithic application to microservices? And the other question is it worth splitting the monolithic application into microservices if they will all depend on the database which you have no access to? Oh, sorry, not the access, but that you have no right to change.
Okay. First thing, how you change a monolith to microservices. That's something where an entire conference can be organized about. It actually depends on your situation. I believe the best thing is to do small steps. So find an isolated part of functionality that you can pull out of this monolith and put into a microservice and start with that. And then change all other applications that use the same functionality to use the microservice instead of the monolith, and so on and so forth. Other questions? Now I have a question for you. Who of you are actually using microservices today? None. Oh, some? Okay, great. And who of you want to be using microservices? Okay, that's a lot more. Great. There's another question?
What about performance overhead when comparing monolithic applications to microservices? Do you take this into account? Do you measure and analyze the performance? So what do you take into consideration when thinking about it?
Of course, there is some overhead with microservices, but we're in a situation where performance is not very critical, in the sense that if an API call takes below 100 milliseconds, we're usually satisfied. So if you're in a more performance critical application, then you would just need to do some tests, because it can, the thing about a monolith is that usually when a API call comes in, that's handled by a monolith on one server, so this entire API call is handled by one server. But with a microservices setup, architecture, you can have one API call that puts 1 million messages into a worker queue, and 1 million servers start working on that API call. So you can have much faster response in that case, but it totally depends on the use case. Okay.
Yeah. What about development machines? When you have microservices, usually you need to spin up 4, 5, 6 microservices, which slows down the development. Are you looking into mocking of APIs or some tools or whatever? What's your opinion about that?
My opinion is that microservices should be contained enough to be started alone, and if you develop on one microservice, you only need to start that one microservice. You need, for example, the RabbitMQ console open to send messages to your own microservice running on your own machine and view the replies. If you're working on a larger ecosystem, the general idea is to put every microservice in, for example, a Docker container, so you can spin up these images really fast. However, that doesn't change the memory overhead, for example, you have for each Java virtual machine you start.
Yeah, thanks.
My question is more from the operational point of view. If you take this approach, how much longer or more expensive is the project because of the I mean, the flexibility and everything that comes, which is pure benefit. I mean, obvious
Yeah.
benefit probably comes at a cost.
If you have the infrastructure up and running, I think it actually saves you time and money. And the thing is that you need to have this infrastructure in place, and you need to have developers that know how to work within this. And you need somebody who guards this microservices architecture in the sense that that not somebody is making this microservice too small, too large, or does strange dependencies or other things that make developers unhappy.
Thanks.
Other questions? Yeah, someone over there.
Hi. So my question is more regarding the architecture overall. When developing, for example, if you have different, let's say UIs, or you are using some mobile devices and other things, so do you have a separate like entry points, API gateways for different devices, or you have one for everything?
We have one gateway, one infrastructure for everything, but we do have separate endpoints for different devices. For example, the website, we have a namespace called dashboard, which where you can request the things you want to show on the website, like a dashboard, like an overview of stores with the dates of their latest Rfid stock count, what the differences were, and what the total number of items scanned were. Those kind of things would be way too slow if you would have to, per store, request this information. And therefore we created a namespace called dashboard that has APIs that where the website can retrieve this information, so it only has to do one API call to show this page.
Thanks.
And actually, maybe it's good to mention is that these dashboards, the information is pre-calculated. So if you request a page, it's really fast. And that's because if something changes, like I just mentioned with the unified log, if an Rfid count comes in, if new ERP count comes in, whatever, then the dashboard calculates automatically these figures as soon as the information changes and not when it's requested.
Okay, you said you use black box testing. Do you use integration testing, and what tools do you use?
Of course, we do unit testing. We also do integration testing, also using a JUnit. And and we use black box testing.
And what tools is for black box testing?
It's actually just a Java Spring Boot application, just like the other microservices.
Okay, thank you.
Have you considered maybe doing automatic starting of microservices, when you have too much load, to just automatically spawn new services?
That's something that we certainly look into, but that's not needed at the moment. We have enough server capacity to handle the traffic we currently have, but that's certainly something we will look into when for example, we have a lot of RFID stock counts coming in at Monday morning, because that's when most of the stores do their count. So these dynamic load balancing, so to say, would be useful to, on Monday morning, have extra microservices processing RFID reads, and the rest of the week, for example, have extra services creating management reports or the things that are not time critical.
Thanks.
Indeed. No more questions? Oh, right.
Hello, my question is, how long approximately did it take from the monolith service to transform to a group of microservices?
Well, actually, we started with microservices. We never had a monolith.
Good choice.
Yeah. But we are working, I think, about 3 years now on this application.
Just one short question. Did you ever have a situation in which services which you developed had recursive dependencies? So basically, maybe you could say it's a poor design or it's a mistake in architecture, but during the development, you had a need, for example, to one service to highly depend on another, but you also had a backward dependency. Did you have any similar situation?
No, we have not experienced that. We try to avoid that by using versioning for all our endpoints. So if an endpoint changes and it's a backward incompatible change, then we create a new endpoint. And we have to keep supporting the old endpoint until all other services have updated to this new endpoint. And as you say, we are desperately trying to avoid these kind of close link dependencies.
Thanks.
That's it? Oh. More questions. Great.
Just when you thought it's over. So one question. Are your services stateful or stateless? And how do you maintain overall state of the system? Meaning you have separate nodes, so to say, and they have to perform something. And if some specific service, maybe it is not in error state, but it is not in the correct state that I need for processing for a current state of the overall system. So do you have some state machine or anything?
Actually, we don't. All our servers are stateless, and everything is linked together asynchronously using message queues. The only thing that has state is the session you have with the website.
All right, thanks.
Last one.
Okay. I like questions, and I get to learn something as well.
Yeah, you had an example with two databases. When from RabbitMQ you receive an event, and imagine that you need to store in two databases and one fails. How would you roll back, for example, the first one which is already in database?
We don't roll back. We just try the failed one again.
Mm-hmm. Okay. Good.
Okay. I would like to thank you all for your attention. And please rate me.